Hello,
Hello.
this is Dr. Rubin.
Rachamim Rubin, not a doctor yet, but
Okay.
I have a master in physical chemistry. So what we did here, it's mainly a thermal energy uses for solar thermal uses. And part of the project was storing energy.
Mm-hmm.
Part of them are let's say production of material that contain high energy levels, like pure metals like zinc, aluminium. They are containing a lot of energy. Trying to produce hydrogen and making a cycle, what we call forming methane. It means you store the energy in a chemical reaction, endothermic reaction, and you have a product. You transfer the product to the user. They make the reverse reaction. It's exothermic, and all the energy released at the users. So they can bring back the material to refill it with the energy. Since the materials was CO2 and methane, or you can use CO2 and steam, and the product was CO and hydrogen, what's called syngas. So you can use the syngas as a source for production of methanol, or syngas you can make the reverse reaction and get CO2 and steam. That's way, because the sun is always shining on the world. 24 hours a day the sun is shining. Mm-hmm. But we feel like halfway of it. But if we can transfer energy from one half to the other half, let's say from the Sahara Desert to Europe, or from the China Desert to other places, Australia Desert, and so on, you can use the sun 24 hours. If you have a net that you see the size of the field that you need to fulfill the all energy uses around the world was about 450 kilometers square. It's not so big. It's a dot on a globe. So if you have 4 or 5 like this connecting together, starting in Australia, moving to China, moving to the Sahara Desert, and then moving to Mexico Desert or Texas Desert, and you have 24 hours.
Constant.
That's the idea of the Professor Israel Dostrovsky, the late Israel Dostrovsky. But that's the idea. You have enough sun. You have enough energy from the sun. The amount was in 3/4 of hour. You have enough energy for the whole world for 1 year. 3/4 of hour of sun, I think. You have enough energy for the whole world for a year. That's amazing.
Amazing. That's the exact word. Amazing.
That's an amazing amount of energy. But some problem, it's dilute. You have to concentrate it, and it's spread not equally. It's it's not uniform spread. You have to move it to one side to other side.
Mm-hmm. Mm-hmm.
That's why most of our research was to solve those transportation, storage, and then as you go up with the temperature, you can be, the Carnot cycle give you higher efficiency if you go up with the temperature. So we try to develop receivers that can work at 2000 degrees or above it, even so above it. And the main receiver that we developed was called a diaper. It's like for a baby diaper, but it's a direct annular pressurized irradiation receiver. Please, I have and it's I have a photo, a picture of it. No, not here. Let's call it.
I can
like
add
a porcupine.
later.
It's a porcupine sitting on a dish. That's was our icon. A porcupine sitting on a dish with a diaper.
Uh-huh. And the diaper stores the energy?
No, the diaper is a receiver that gets the energy. In the diaper, the diaper is unique because it has a transparent window, and all the light goes into the receiver, and you can have heat transfer with higher efficiency. Because at first we work with a tubular receiver. Then the heat goes to the wall, the outside wall, until it goes in, and you have losses all the way. And with the diapers, all the energy, all the light goes in, because it has a window, quartz window. And quartz window has another benefit, because when it's hot inside, it radiates the infrared, and the infrared was blocked by the quartz, because the quartz is observe the infrared radiation. So most of the energy is staying inside the receiver, and so this receiver, we managed to connect it to gas turbine, and we managed, and also there's a pilot that they try to build in Israel at near Yotvata, at the kibbutz Samar. There's a small tower. I don't have now all the important figures, but
I can get after you talk. Yeah.
okay. And we also develop a receiver that the gases that's inside was about 400 degrees hotter than the wall of the receiver. Because usually the wall are getting much hotter, and the gas temperature is lower than the inside. But what we did, we took a receiver, and the string was gassed with fine particles of carbon, with 3% of carbon particles. And the carbon particle observe the light, because they are black, and they transfer immediately the energy to the gas. So the light is not hitting the walls, because the particles behave as a screen from the light and the walls. And so they observe the light before the light going to the walls. And we get the temperature of the gas is about 1900 degrees, and the wall about 1400 degrees. Because the problem when you go to such a high temperature is the material problem. You don't have much material that can stand.
Right, will melt.
And stand 2000 degrees. The other project was reduction of metal oxide, like zinc oxide, to zinc with the carbon. It means you have a batch of zinc oxide, mix it with carbon particles, then heat it with the sun, and you get a metal of zinc. The metal of zinc is a source of energy. All batteries are made of zinc.
Right.
And also you can do it with magnesium. Magnesium is much harder, but also you can do it we did it with aluminum oxide.
Mm-hmm.
And it's work, and we prove that
to be able to store the energy, so that
you can store the energy, and zinc you can transfer
Mm-hmm.
anyway. And the reforming methane, as I told you, is also, it's not our original idea. This idea comes from the German nuclear sites. They store the energy in this methane and CO2. It's called this cycle called Eve and Adam cycle. And but there in a nuclear receiver you have a constant, and you control the energy.
Mm-hmm.
But with solar, your fluctuation can be from minute to minute. You can get many fluctuation, and we managed to do a real test with 100 cycle with the same material, with the size of 10 kilowatts. That was in a solar furnace that we did. The one very unique project was the late Professor Avram Kogan tried to split water to get hydrogen and oxygen. And there was no problem of reaching the temperature of splitting water without anything. Get to 2000 degrees and you get the water start to split. But you have to separate the oxygen from the hydrogen.
Mm-hmm.
How you do it? You need a membrane, but you need the membrane to be the membrane that can bear 2000 degrees. But he tried to develop it, and with the help of the technion, they developed a membrane that can stand for quarter of hour, and they managed to split water, but after quarter of hour, the membrane was stopped to separate. So all the holes
Mm-hmm.
that make the separation or get weaker and he moved to split of methane, because methane is contain a lot of hydrogen relatively to the because it's one carbon and 4 hydrogen.
Okay.
If you get ethane or something like this, the ratio is
Lower.
Mm-hmm. And you start to split methane, and you get a dust of carbon, and he make some calculation. It says that the amount of hydrogen that I have, it's not commercial benefit. Mm-hmm. It costs too much to produce it. But when you check the powder of the carbon, it found out that the carbon is cost much more than the hydrogen. You can throw away the hydrogen.
Okay.
Because the size of the particles was so fine, and in some industry like tires industrials and graphite industrial are need this fine particle, and they pay a lot of money to reach the size of the particle because these particles are produce in situ the reaction between, and they don't grow too much. And one day when they test the particles, and they found some nanotubes of carbon. And nanotubes of carbon is relatively very high, very new science, and many trying to produce nanoparticles, because a lot of things in computers and medicine can use these nanotubes. And but this also was stopped. And what can I add? If you have any questions, so something, I would like to answer.